So our next speaker is Yeng Saanchi, and she is a relatively new tester and new to the JMP organization. She's going to talk about applying these test methods to testing the prediction profiler. So go ahead.
Good morning. Thank you for coming. As Tom said, my name is Yeng Saanchi, and my presentation is about validating the prediction profiler with disallowed combinations. This is joint work with colleagues whose names are listed below. But before I jump into the actual presentation, I would like to tell you a story to provide some background. So many years ago, in the profiler city of the JMP world, there was a problem that many of JMP's allies had complained about, and this was the problem, that certain disallowed entities were allowed to breach the defenses of the city when they should not. So their complaints were heard, and a band of valiant knights was assembled to tackle this problem. So here begins the tale of validating the profiler with disallowed combinations. What is the prediction profiler? The prediction profiler is an interactive tool in JMP that enables a user to explore relationships between multiple responses and multiple factors. It is commonly used to explore the predicted model of a designed experiment. And it is displayed as a set of univariate plots for each factor that show the predicted response settings of the factors. A user is allowed to interact with these plots to change the factor values and see how the response changes accordingly. It is often used in conjunction with the desirability function, which is a widely used approach that involves assigning a scale-free factor between 0 and 1 to a set of models which involve multiple responses. So suppose you wanted to optimize several responses at the same time with perhaps different objectives. The desirability function approach is a common way of doing this. The maximized desirability option is a very important feature in the profiler, and we'll see in the next few slides what that looks like. So here is what the prediction profiler looks like in JMP. So here we have one response and two factors, A and B. The user can move the crosshairs to the left or to the right to change the factor values and see how the response changes accordingly. The function governing the response is shown above. Now, this is how the maximized desirability option works. So here in this particular example, the response goal is to maximize the response. Now, when we select that maximize desirability option in the profiler, an optimization routine is run. And here in this example, we see that our response is maximized when the factors A and B are at 1 and -1 respectively. So what are disallowed combinations? For our purposes, a disallowed combination is a Boolean expression that evaluates to true if a given design point is not in the design space, and evaluates to false if the design point is in the design space. We typically use these to create designs where the runs consist of only points in the allowable region. Disallowed combinations can be relatively simple, such as combinations of levels of two factors, as we can see there in the first example, or they can be relatively complex, such as several disallowed combinations that result in a very complex non-convex design space like a map, as shown. Now here's an example of a disallowed combination. In this example, we have 5 responses, 2 3-level categorical factors, and the disallowed combination is that X1 and X2 cannot be at level 1 at the same time. The profiler was recently enhanced to obey disallowed combinations. I'm now going to play a video that will show you how the profiler worked before the enhancement and after the enhancement. Now, the data set we use here is generated using the custom designer in JMP. It consists of 2 3-level categorical factors and 1 continuous factor, and there's 1 response. The disallowed combination is X1 and X2 are not allowed to be at level 1 at the same time. You'll see in this first example that The profiler completely ignores the disallowed combination. That is, the user can move x2 to L1 even when x1 is already at L1. And when you maximize desirability, the optimal settings shown have x1 and x2 at L1 at the same time. Now, this is not what we want, and this is not what users want. Now, in the current version of JMP, we will see that the disallowed combinations are obeyed. A user cannot move x1 to L1 when x2 is already at L1. And when we maximize desirability, the optimal setting is within the allowable region. We use the same data set as in the first, the unenhanced version of JMP. And you'll see this shortly. Wait for it. So once you move x1 to L1, L1 is not an option for x2 anymore. The user cannot move to that region. And optimizing the desirability, that's where the magic happens. The optimal setting is in the allowable region. Okay, moving on. So what was our task? Our task was to ensure that the prediction profiler was indeed honoring disallowed combinations. So a team of developers and test engineers with different backgrounds was assembled to do this. And the team had originally been investigating how to ensure that the maximized desirability option in the profiler was honoring disallowed combinations. So most of the team members already had sufficient prior knowledge about the inner workings of the profiler and what validating this enhancement should entail. What is software testing? As Ryan mentioned earlier, there are several definitions, but the adopted definition of the team is that of Myers, which says testing is the process of executing a program with the intent of finding errors. What then was our challenge? So the field of statistical software testing is fraught with many challenges, and I will enumerate a few of them. One challenge is determining what constitutes an error for a given test case. In other words, the test engineer must ensure that he knows what the expected outcome should be so that any behavior that deviates from this expected outcome is deemed a failure. Another problem the team faced was the paucity of a variety of data sets to ensure adequate coverage of all the possible inputs that evaluating such an enhancement should entail. Thus, the team had to decide which inputs to use in our test case, and given the several possible combinations of the levels of these inputs available, the subset of these test cases to actually test. So we really are faced with a challenging problem, and you will see this as we go on. Now, our goal was to find bugs. So where are those bugs? Again, we borrow a quote from Beiser that says, "Bugs lurk in corners and congregate at boundaries." Now, this quote of Beiser's implies that bugs in software testing are usually as a result of incorrect implementation that involve multiple inputs and not just the individual inputs. Thus, our task was focused on finding the failures that were precipitated by interactions between multiple inputs rather than individual inputs. So our testing approach, we chose the use of combinatorial testing using covering arrays. So this ensures that our design region the region for testing is covered within the least possible number of runs. And Ryan explained earlier how covering arrays help us to do this. Now, why covering arrays? Because they are cost efficient and effective. they help to alleviate the selection problem. That is, faced with a vast number of test cases to choose from, they really shrink the size of our test cases to make them actually a feasible task. They also enable us to find failures that are due to the interaction between multiple factors and not just individual factors. And they are also a very disciplined and defensible approach to testing as against, just testing more, which is a more uncontrolled and approach that usually has no rhyme or reason. Because I could choose a set of test cases and my colleague could choose a different set of test cases and so on. And, that really is, in my opinion, quite uncontrolled. Okay. So what do we do now when we're faced with the limited variety of data sets to use for testing? And different users have different needs and different ways in which they use the profiler. So how do we account for all these? Our solution was to combine dataset generation with test case selection using combinatorial testing. And after much deliberation, we settled on 15 dataset generation factors and 3 test case selection factors. So here are the dataset generation factors and test case selection factors that we decided upon. Basically, every row in this dataset suite, these are the factors that were used to generate our data sets. So the first 4 factors are actually 2-level categorical factors that consists of the levels, either 3-level discrete numeric or 3-level categorical. The next 6 factors are either all categorical factors, all continuous factors, or a mix of the two. Then we have the number of responses, the response goal, which is either to maximize, minimize, match the target, or a random selection among them. Then we have the model that was used to generate the design. Then we have our constraints. We have continuous constraints. We have linear and nonlinear ones. Then we have the run size, that is the number of runs in our design. Then whether to augment the design with additional runs or not. Then we have the model that was used to simulate the response. Then the last 3 factors have to do with the profiler inputs. We have the maximize and remember option. We have the number of times that maximize desirability is run, and the sensitivity indicator. This is a control in the profiler, which enables a user to quickly see sensitive regions in the design when faced with a large number of factor profiles. So, given those factors that I showed in the previous slide, if we look at all possible combinations of the levels of those factors, we have over 1 million possible test cases. Now, I don't have sufficient time and resources to be able to do all of that. However, a strength 2 covering array has all pairwise combinations of these factors covered in 13 runs. And all 8 combinations of the profiler inputs are accounted for in this test suite. So here's an example of a data set generated using one row of that covering array. So remember that for the covering array, the columns are the inputs, the factor inputs, and then the rows are the test cases. So one row of the covering array enables me to simulate a data set that would then be used to test the profiler. Okay, so in this particular example, I have 5 responses, 2 continuous factors, 9 3-level categorical factors, and 1 discrete numeric. So other than the obvious thing to test, as in such as whether the software crashes when I launch the profiler, there are other aspects of the profiler that we have to pay close attention to, such as whether the profiler displays the constrained region correctly, whether the profiler only profiles allowable regions, whether the profiler options work as expected, whether the profiler exhibits a lag in profiling when the user interacts with the controls, and whether maximizing desirability finds the optimum in the constrained space. Now, some of these are important but fairly straightforward to test. For instance, a user interacting with the controls in the profiler would not like to wait not like to experience a delay when he moves the crosshairs to either the right or the left to see how the response is updated. Now, this is a very important thing to check, but it's also fairly straightforward. There are implementations in JMP that enable us to do this fairly easily. Now, one feature that is much more challenging to test is whether maximizing desirability finds the optimum in the constrained space. Now, this is challenging because the constrained space can actually be very unpleasant, and it's very difficult to find an oracle, like what the expected outcome should be. Sometimes a test engineer has to use alternative software, but this can be time consuming. Sometimes an analytic approach can be used, but sometimes your problem is such that there is no analytic approach, and so you have to find a workaround. So for our test cases in particular, using an alternative software and using the analytic approach were not options. So the team decided to use the desirability measure approach because we thought that it would be more general and efficient. And I will explain what I mean by this. So we simulated our data such that the expected maximum desirability is 1. So once we tested the optimization routine, the actual desirability measure, if it was within 0.05 of 1, we allowed the test to pass. And of course, we had to make sure that the factor settings were within the constrained region. Now, the optimization routine that was developed to do this optimization is actually a genetic algorithm heuristic, and it is guaranteed to find an optimum that is as close to the global optimum as possible, but not necessarily the global. So a constrained region could be a very complex non-convex space that has several local optima. And it is possible that even within, by the time the optimization routine has reached the maximum number of iterations, it would not have been able to find the global optimum. It would only be able to find one of the several local optima that may exist. And so we thought that using the maximized desirability factor, which we already knew what it should be, if it was within 0.05 of 1, we accepted the test as a pass. Also, if maximization was done multiple times, we only allow the test to pass if the most recent desirability was at least as good as the previous one. I cannot conclude without talking about the sequential nature of testing. This simply means that the team went through several iterations of testing even after the initial phase of testing. And this enabled us to actually capture a fair number of subtle failures which would otherwise have gone undetected, such as anomalies in the profiler traces when the design matrix is singular. This was done using JMP's nightly unit testing framework, which enables us to do regression testing, which, as Ryan said earlier, is ensuring that the software continues to behave as intended even when there are alterations in code. We also revisited the oracles in order to ensure that what we had initially set out to be the expected outcomes was actually correct. We're doing the right thing. And then several meetings led to improvements in our test suite, such as using data sets that were generated not using JMP's custom designer, changing the genetic algorithm options, and then allowing for different specifications of the disallowed combinations. So, the highlights. Testing statistical software is challenging. Why? Because deriving oracles is quite difficult, and there are usually not enough data sets to ensure adequate coverage of the possible users of the software or the features that we are trying to test. Combinatorial testing, however, is effective and efficient because it allows us to capture failures that are due to interactions between multiple inputs. It also helps to alleviate the problem of deciding what subset of test cases to select for testing. And generally, it's great, really. It helps me a whole lot. So this case study is it actually revolves around the novel idea of combining both dataset generation and test case selection in validating the prediction profiler using a combinatorial testing approach. Thank you for your attention.
Great. So we'll take some questions here, but I have one online, so let me start with that. This person's asking, if I am analyzing data in a table that isn't created from a JMP design or was derived from one, but doesn't have the design scripts, how does the analysis profiler know what I intended as disallowed combinations?
Well, I believe that there is, you have a data set, like she has a data set and she has some idea what the analysis should be. So there are analytic routines in JMP that enable us to analyze data. Like there's the analyze menu that has a whole bunch of models in there. Now, if you do that, if you run a model, let's say a simple one like linear regression, you have the factor profiles there. Now, right now, JMP is enhanced to honor disallowed combinations. So suppose there were disallowed combinations in the data set. I believe that the factor profiles will show it. They would need to add it. The disallowed combination, okay, within the, right, but the question is they don't know what the disallowed combination is. Mm-hmm. Oh, they do know what, okay, then that is quite.
Yeah, I have a solution for this. So what I would do is I would fake creating the design in the custom designer and set up the disallowed combinations there, and then create the design. It would be a new data table, and then I would just copy the disallowed combination script that's attached to that table over to the table that they brought in from someplace else, and that would communicate the disallowed combinations to the profiler, so you could take advantage of the what Yeng was showing here with the profiler.
Great. Are there questions in the room now? Well, I was just going to say, if nobody had them, I was going to ask one. Let's start with this gentleman.
Yeah, sorry, this is a short question, but I'm used to using disallowed combinations with designing tests in the first place, and so I have a concern for the case where, well, what if we have a test where we designed for disallowed combinations that we couldn't test at, but we still want analysis of, so there's some sort of extrapolation after we do the test, and we don't want that piece cut out in the prediction profiler. Is there capability for us to then remove that easily, or remove the disallowed combinations then after we've already established this data set to have them?
You mean add the disallowed combination after the fact? Like take it out
remove them after the fact. We designed with the disallowed
Oh,
combinations, but then
okay.
analysis we want to actually be able to again, so suppose we have some sort of danger area that we can't test in,
Mhm.
but we still want to see, with extrapolation, how much do we understand in this area, or something to that effect.
Brian, well, okay. Sorry, Chris.
Yeah, or just, yeah, I mean, in some sense you can remove it or change the name of the table script. So I mean, it's probably not a bad idea to keep it there as a reference, but so the profiler is just looking for disallowed combination, the script name in the data table. Right. So then it would behave like the old, then it will potentially maximize in the, yeah.
Yeah, I guess that a quick question is, huge fan of the covering arrays and what's in JMP Pro and the default of even being able to do the analysis piece, right? So you get to go right into association analysis, which isolates and kind of find your problem pretty easily. So my question is, are there other analytical methods on the analysis side? The design side, outstanding, and association analysis, darn good, but is there something else?
I'll say we're working right now with some people at Duke on a new framework. So it's coming.
So thank you for introducing me to covering arrays, at least. I love it. As a tester, I often am looking at validating more complex simulations. And I was wondering if you have a binomial response for that simulation, if covering arrays would be appropriate in that case, or if you only envision it for software testing.
A binomial response? No. So actually, covering arrays, at least the framework in JMP, actually accepts only categorical inputs. So the way we went around working around the continuous was to do some equivalence partitioning, if I remember correctly. But when you say response, what do you mean? Because pass fail. Oh, so that's a categorical factor. And so, yes, that is perfectly doable. Yes, yes. Mm-hmm. Yes.
Still have a couple minutes. Are there any other questions in the room? I have one more. I noticed in the examples that you gave and even what Ryan was showing that you showed that you could do, strength 2, strength 3, 4, 5, 6, but you typically seem to do just 2 or 3. And it looked like if you could do 4, you could get an even higher level sort of assurance. Can you just talk about the practice of why maybe you're just showing 2 or 3?
Because the lower order interactions are usually more important. And you have to weigh, how much benefit you get from just adding more. In Ryan's slides, you would have seen that even in the strength 2 covering array, you could get 75% of coverage for a strength 3. And I think that is a decent enough coverage given the time constraints and the resource constraints, really.
So my question kind of gets to the resource. I mean, if you're talking about there's millions of combinations and I can do this in 14, well, what if you could have done 100?
Oh, if I could have, then...
I mean, how expensive is it to do one of these tests? And, could you just do it?
Yes, you could. And you could always add on more rows to the covering array, depending on, suppose, like the covering array gave me a certain test suite, right? And then I identified that there was something else that was not in there. I can just append it to the covering array. There's nothing wrong with that. I still retain the coverage that I originally had. In fact, improved upon it.
Okay, are there any other questions or comments in the room? Well, then let's thank our speaker.